All right, substitution reaction of alkanes. Before I proceed any forward, remember that this reaction falls under many different categories. So if we are mentioning it as a substitution reaction, first and foremost, what's written over here, yeah, that's right, because we are going to replace every hydrogen with a halogen atom step by step, one after another in subsequent reactions. So yeah, substitution. But apart from that, sometimes we place it in a category of photochemical reactions. Yeah, that's pretty much possible since the reaction is initiated by sunlight. So it's a category of photochemical reactions. We also sometimes place it in a category of halogenation reactions. Understandable, this is actually halogenation reaction. Halogenation means reactions with halogens. So yeah, alkanes do react with halogens in the presence of sunlight. So it do fall under multiple categories, and we have studied the same categories back in IGCSE. Now, if I talk about the reaction, this definitely requires a mechanism explanation. So, alkanes undergo both substitution. We have taken the example of ethane and chlorine under sunlight. This reaction is going to go forward and produce a halogenoalkane. This does not happen in darkness. How do we prove it? We can prove it by a simple mechanism. Take an alkane, take bromine or any halogen, mix and leave in sunlight. If the color changes, it means it's positive. Reaction proceeded. Bromine have no color, hence the colorless experience. All right. If we mix and place it in a dark cupboard, there is no reaction since bromine will show its original orange brown or yellow brown color. Make sure you go with orange brown or yellow brown. You don't go with red brown. Why? Because we do not use pure bromine with it. We use bromine water for the purpose, and that's a little bit of a dilute color over here. So for that orange brown or yellow brown, yeah, the color stays the same. The bromine does not decolorize because the bromine is not converted into an organic bromo product, right? So this is the easiest way we can prove the reaction. As far as the mechanism is concerned, we have three steps for the mechanism. The very first step is initiation. Initiation itself is the photochemical step of the reaction. Now you'd notice that because of the presence of sunlight or UV light, what we do is that we convert a molecule into radicals. I'm specifically placing a plural. Why? Because there are more than one radical produced. In this case, chlorine molecule is converted into chloride radical. In order to explain this reaction further, what we do say is that this chlorine molecule is made up of a single covalent bond. That single covalent bond breaks in such a way that the respective electron of each chlorine atom goes back to it. Of course, this is actually a shared electron pair. If every electron returns to its respective owner, we will form a radical. So how do we define radical? In the previous chapter, we define it as any species which contains a free unpaired electron. Unpaired electron means that orbital will be half filled, it won't be completely filled. Remember, for any orbital, there should be two electrons for the orbital to be completely filled. Hence, half filled means unpaired electron. We show it as a dot on top of it, not exactly to the side. It's actually a printing mistake of the book. The dot should be up top. So we use curly half arrows, fish hook arrows to show this kind of electron movement. You do not show a double arrow because double arrow means differently. So don't use that. All right. Moving on. Now, as the Cl bond breaks, each chlorine atom takes one electron from the pairs of those electrons. This is an example of homolytic fission. Now remember, homo means same, lytic means breakdown. Homolytic fission is kind of a breakdown of the covalent bond where the electrons were equally or mutually separated between both the atoms. So both tend to keep one electron each. So unpaired electrons with both Cl atoms, we call them radicals. I just explained it. So moving on to the second step, which is the propagation step. The word propagation itself means to go on, keep moving on. So the propagation steps means the reaction keeps moving on. Now, free radicals are very reactive. They will attack normally unreactive alkanes, and a substitution would be proceeded in such a way that a molecule reacts with a radical and it produces a radical and a molecule. So molecule plus radical gives us molecule plus radical is something that we can easily write for a propagation reaction. Now, for every different type of reaction, propagation reaction, you'd notice they're always given in two steps. And in both the steps, this scheme remains the same. Molecule plus radical gives us molecule plus radical. So radical, molecule, molecule, radical. In this specific case, notice that the C2H6 is attacked by a chlorine radical. It gives us an ethyl radical, C2H5, and it's important that you put the dot on carbon and not hydrogen because carbon has the unpaired electron and not hydrogen. So make sure your dot stays on the specific atom that has the unpaired electron. Plus, the hydrogen that got substituted out of it reacts with this chlorine and tends to have the HCl made. So this reaction doesn't stop over here. The same ethyl radical that we are talking about gets to react with another chlorine molecule and produces for us the compound CH3, CH2, Cl, or we can simply write, since I'm writing a somewhat differently from the book, because you should be familiar with this kind of convention. You should be familiar with this kind of writing convention, writing C2H5 together or CH3CH2. You should be familiar with both. And this reaction also produces a chlorine free radical. All right. So again, it produces a radical which can go out and attack another molecule. So the reaction propagates. This regeneration of radical actually uh, itself goes with the word propagation. Propagation is the word that we commonly use in biology for growing new plants, since growing new plants completely depends upon cell division. So the same thing happens over here. It completely depends upon the regeneration of the free radical for the reaction to move further. I hope this makes sense. I hope this also connects to what you have previously studied in biology. Now, if you understand these points, remember this is not how it would stop over here. The same molecule, for example, this C2H5Cl can be further attacked by the same radical. See, it would give you C2H4Cl as a radical. Take one more hydrogen out, and it's going to produce HCl. Now, the C2H4Cl can attack another chlorine molecule. And since this is a radical, let's put the point over here. It's going to form C2H4Cl2, plus it's going to give us a new radical to propagate. The point I want to make, and notice that point, we started off with C2H6, take one hydrogen out, replace it with the Cl, that's what you get as the first product. Take one hydrogen out, replace it with another Cl, that's what you're going to get as the second product. The reaction keeps on continuing, so much so that you get C2H3Cl3 is the next product. Take one hydrogen out, add one more chlorine. Then you're going to get C2H2Cl4. Again, take one hydrogen out, add one more chlorine. So much so it leads towards C2HCl5 and finally C2Cl6. So much so every hydrogen present in the alkane will get substituted with the halogen, in this case, chlorine. Hence, You have this whole paragraph to understand. Now, there are many points in this paragraph that are important to understand. This reaction is not really suitable for preparing specific halogen alkanes because we get a mixture of products every time. And for simple alkenes such as ethane, I've shown you one, two, three, four, five, six different products. And of course, this reaction would proceed and keep making more and more products. That's why you get a different set or mixture of products. So this reaction is not really good. If you're thinking about producing one specific product, let's say we would like to mark this specific product we would like to produce, this is not a good reaction. Do not choose this reaction for the production of any specific products out of these. Why? Because every time you're going to go with the reaction, you won't know. Place both of the elements in both of your reactants in sunlight, and what mixture it's going to produce, it's always going to be a mixture. You won't know. And since you won't be able to produce one specific product and stop the reaction at that, that's why this is not a good choice. So notice that it produces, and this one in specific is chloroethane. This one in specific is dichloroethane, right? And of course, next one would be trichloro, tetrachloro, pentachloro, hexachloroethane. So notice that this reaction may include different products, 1,1-dichloro or 1,1-trichloro, or maybe their isomers, 1,2-dichloro or 1,1,2-trichloro, or maybe a tetrachloro, and so on and so forth. It would produce chloroethane like that. Means all possible products and probably the possible isomers as well. Now, if there is enough chlorine present, remember, if we have a higher amount of chlorine, if we have an excess of chlorine, we'll eventually get hexachloroethane. So much so we'll get to the last product I mentioned. Now, this variety of chloroalkane products results from the propagation steps in which we keep on producing one chlorine-free radical after we form a chloroalkane. So do understand and do be capable of writing any of the products that they ask for. Okay, because the possibilities are limitless. The simple products that we can think of and the isomers we can think of as well. Make sense?
Yes, sir.
Good. Now, if this makes sense, the more chlorine gas in the reaction mixture to start with, the greater the proportion of chlorine atoms in the chloralkane form. And I should explain this. If you have more chlorine gas, or if the examiner has mentioned a bigger mixture, a bigger amount of chlorine gas in the mixture, do understand the point that you're going to get these products more. And if you have less chlorine, you'll get these products, this one or this one or this one more. Means the products with less number of chlorine atoms, we get those products if we have lesser amount of chlorine in the reaction. And if we have an excess of chlorine in the reaction, even with the higher pressure, we tend to get the products with more amount of chlorine atoms per molecule. So he has already given us the hint what's going to happen. But there must be some way in order to terminate everything. And yeah, that's how we cater termination steps. A termination step is a simple radicals, two different radicals or even same radicals can give you a molecule. Now, this is exactly opposite of what we started off with in initiation. In initiation, a molecule was producing more than one radical. Now, more than one radicals are reacting together to produce a molecule in termination step. And this can happen at any time. And in this case, a single molecule is the only product. No radicals are made in this reaction. So notice the chances are ethyl radical, chlorine radical or product, or maybe two ethyl radicals for butane, or maybe even two chlorine radicals for a chlorine molecule. But since this is what we started off with, we tend to not write this reaction in termination. We usually write these reactions in termination. These are just example reactions of termination. The point we're trying to make is that we can write the reactive free radicals, such as chlorine free radical, along with the radicals that are formed from our counter reactant, in this case, ethyl free radical, or you can say C2H5 or C2H4Cl, any of those radicals can work. If a radical reacts with a radical to produce the molecule, this would be a termination reaction. Does not matter which radical you are reacting it with, because this is the only way in the sequence where the chain reaction stops, as mentioned in the explanation over here. I hope this gives you the idea that the initiation and termination are completely opposite to one another. Okay, do understand the point when we talk about ozone, which we have talked about in previous books a lot. There is a blanket. The gas is O3. It's acting like a blanket. It's covering the entire planet Earth in such a way that it's actually blocking this planet Earth from the harmful rays of the sun, the harmful UV rays. And actually, those UV rays help them for the oxygen to be converted to ozone at that point. Now, we have been saying all along that this ozone can react with the chlorine radical and can be converted into oxygen at that point. And it's really harmful if the ozone at the point where the blanket exists at this point is converted into oxygen, because at that point, oxygen is of no use. Ozone is. And below in the atmosphere of the Earth, in that atmosphere, ozone is a real problematic gas. It gives us respiratory issues. Is really harmful for people with asthma. So, yeah, oxygen is like a blessing, the gas because of which we all exist, and ozone is a problematic gas on Earth. However, at the point where the blanket exists, talking about the stratosphere, ozone is the blessing gas. Ozone, oxygen isn't, right? So if we talk about this, and this has been an example in previous papers, especially the papers before 2016, so you'll find the same thing. Now, this example will clearly give you the idea that initiation actually comes from the breakdown of chlorine molecule into radicals. Propagation is the step where ozone is destroyed into O2. And in that specific example, the point why I picked this example is that one chlorine free radical can at least break down 100,000 ozone molecules before it can go with termination. That's an average how this reactive radical can break down molecules before it can hit a termination reaction. The same thing happens over here too. The chlorine free radical can break down hundreds and thousands of molecules of ethane and convert them into products before it goes with a termination reaction. All right. That was to give you the idea why we call propagation a propagation. It really is propagation that keeps on propagating with another molecule, another reactant molecule, and it actually proceeds with thousands and hundreds and thousands of molecules before it gets terminated. So important is the part which I've repeated before. Initiation is molecules into radicals. Propagation is molecule and a radical to give you a molecule and a radical, and termination is where radicals end up in formation of a molecule. Overall, the reaction between alkanes and halogens, and it can be any halogen. So far, we have been taking the example of chlorine free radical, but it can be bromine, it can be iodine, it can be fluorine. But all of those cases, they would involve these three-step mechanism: initiation, propagation, termination, which itself as a whole is known as a free radical substitution. So the reaction of a halogen with an alkane occurs with the help of a free radical substitution. This finishes the free radical substitution part. Any questions from this portion?
No, sir.
No, sir.
Okay. Let's say we have a C3H8 and it reacts with fluorine in the presence of the sunlight, and then we have C3H6 and it reacts with fluorine again in the presence of sunlight. What would be the organic products of both the reactions, and which mechanisms do they follow? One by one, answer both reactions. Take your time. Think about it. Name the product. You can formulate it for yourself. I don't mind you formulating or not formulating it, but name me the organic product and then the mechanism followed for the formation of that product. First of all, in reaction 1, C3H8, then in reaction 2, C3H6.
So the first one, I guess, will be C3H7Cl plus Cl radical ion.
So C3H7, Cl, and
Cl ion. Cl ion.
Cl radical. Okay.
Yes.
Okay. I am simply asking the organic product, so let's not consider it because that's not an organic product. And by the way, I wrote complete molecule, so you're supposed to answer it as HCl.
Okay, sir.
Okay. So moving on, the second one would be
C3H5Cl plus HCl.
C3H what?
5
Uh-huh.
Cl plus
Okay.
HCl.
Plus HCl. All right. So this is so far with the products. And again, I'm going to remove HCl because that's not the organic product. So let's remove it from both ends. And let's talk about the mechanisms. Mechanism for 1. The name of the mechanism would be? This is the name of the mechanism for this reaction. So do you think the same mechanism, free radical substitution, would be used for both the reactions? You have a different one on mind. That's what I'm asking. You don't exactly have to come up with a different name. You can simply tell me which one follows free radical substitution and which one does not. If both of them follow free radical substitution, you can answer it that way. It's entirely up to you. What option
So
will
this
you
is
like to pick?
initiation, I guess.
Free radical
Initiation.
substitution? Okay. This one. What about the second one?
No, the second doesn't follow.
The second one is what?
It doesn't follow free radical substitution. It's an alkene.
Okay, so it's not a free radical substitution. Okay. So you both want to stick with these 4 replies. Can we discuss the reasons now? If anyone has
Yes.
a different reply than what's written over here, let me know. So we can discuss your reasons one by one. No different replies? All right. So I'm going to assume that you both have the same set of replies for all these 4 answers. Okay. Now, For the first one, yes, this one is correct. But what if, and I am asking this from Saad, what if the examiner asks you that the product consists of 3 chlorine atoms per molecule? How would you reply then?
So can you repeat? I didn't understand.
The examiner insists that the organic product consists of 3 chlorine atoms per molecule of the product. How would you reply with the answer then? Let's suppose he gives you a mandatory portion that the answer must contain 3 chlorine atoms per molecule of the organic product. What formula or what name would you come up with?
Trichloro, what you call, propane.
The formulation would be, well, then,
Trichloro,
first of all, good, you're right, correct with the name. So the formulation would be the molecular formula
C3,
C3,
H5,
H5,
Cl3.
Cl3. Perfect. Right, very good. So let's bring everyone on board that, yeah, your first response can be C3H7Cl. It can be even a different molecule among the same series. If it's following the same pattern, yeah, we can write anything. If the examiner specifies the number of chlorine atoms per molecule of the system, go accordingly, because remember the free radical substitution can form a monochloro or a dichloro or a trichloro or a tetrachloro, all the way up to
Yeah.
octachloro substances is possible.
So
Right?
won't the second one be C3, what you call, yeah, C3H4, Cl2, the second one?
We'll discuss that. I'll come to that. Hold on to your answer and we'll definitely discuss it. Okay. So it follows free radical substitution, and yes, that is correct. So at first, this answer, this whole thing is correct. This whole thing is correct all along. Now, this is also correct, and any other answers all the way up to octachloro system are correct. Now, you said this answer, Laiba. Saad, you were just saying it's C3H4Cl2. Is that what you're saying just now?
Yes.
Okay, let me tell you this is incorrect. Let me tell you this is incorrect. And this part is correct. If you think it's not going to follow a free radical substitution, which mechanism do you think would it follow? This is a question from you, both anyone can answer. You're correct with this. So it definitely does not follow free radical substitution. Which mechanism do you think it would follow?
Just a second, sir.
You can take help from the book. I'm even fine with that. You can take help from anywhere you'd like to. That's fine. That's not cheating. Go ahead, scroll the pages of the book, get a compiled answer, take a minute or two for that. That's fine.
Sir, it will make a haloalkane, the alkene
Yeah,
at room temperature.
it would definitely make halogen alkanes. That's fine. That's not what we are targeting. We're targeting the mechanism. Just like you said, free radical substitution, you can come up with any other mechanism that is a part of AS. Now there are nucleophilic substitutions, nucleophilic additions, electrophilic substitutions. There are many things in the part of AS book. You need to name one apart from free radical substitution.
Halogenation of alkenes.
That's not the mechanism, that's the kind of reaction.
So is it electrophilic addition?
Electrophilic addition. Very good. Okay. And do we lose any atoms during addition reaction?
So no, but it is the addition of electrophile species. So chlorine is an electrophile.
In this case, chlorine will act like an electrophile. Yeah, that's right. But we don't lose any atoms, which means both of your answers are incorrect, and the correct answer would be C3H6Cl2. Addition, the best part about addition is this, that this one and this one keep all of their atoms. Substitution replaces one atom of hydrogen with another atom or a group of atoms. That's understandable. So there are two products over there. Addition ends up in a single product. So that single product actually consists of all of the reacting atoms. And it is electrophilic substitution. Oh, my bad. Addition. Electrophilic addition. And it's a part of next chapter. Oh, same chapter. Same chapter, just the next portion, alkenes. So it's electrophilic addition. And we won't lose any atoms. So the answer would be C3H6Cl2. And the reaction may also occur at room temperature. We don't specifically need sunlight for this reaction to happen. All right. Now this is a pre-heads up, but since you might have already studied that part, it would help to joggle your memory. Okay. Now, for another question, for this specific product, half-top for reaction one, let's get back to free radical substitution because this is what we have just started, and you can definitely answer questions more easily from this part. For this specific product, do we need a specific set of conditions for reactants?
So can you repeat?
For C3H5Cl3 or for trichloropropane that you answered, do we need a specific set of reaction conditions? Apart from sunlight, do we need any temperature, any pressure, any concentration points to mention to the
So
examiner for making this product?
excess of chlorine.
Good, excess of chlorine, right? The more the amount of chlorine, the better we can get to the higher chlorinated product. Okay, if I have used a little bit of pressure and if I've used a good excess of chlorine, up to how many atoms of chlorine per molecule can we get to?
Three.
No, think again. 3 is definitely too low of an answer.
5 to 6.
I can get to 8. I've been using the word octa. I might have used wrong by mistake penta, but I corrected myself right there. Octa. Octa means 8. So yeah, we can get this molecule to this state if we have set of right conditions, enough amount of chlorine and a little bit of pressure. You don't specifically have to mention pressure as that's not a part of your book, but excess of chlorine would do the trick. All right, keep that in mind. Are we good?
Yes, sir.
Now,
Yes,
these are as many different uh, things or ways the question can be manipulated in Cambridge about this one. Now, one of the last manipulations, and I need to erase all of this. I'm just repeating it. I've already used that manipulation in one of the questions I asked you people. So this would go for C3H7Cl plus HCl, right? That's how you would answer it. You would answer it as C3H8 plus Cl in the form of C3H7 plus HCl. All right. That's how these two different reactions work. Okay. Remember, this is a summed up reaction of what happens after the whole initiation propagation steps. Since that's not mentioned over here, but that was a part of IGCSE. So I hope you'd be able to write it with the whole chlorine molecule in the presence of the sunlight, where we need to write the whole reaction, not the steps of initiation propagation separately. And what if we need to write the propagation steps? The first propagation steps work like this, the one written below. I hope now you're capable of differentiating them both. That's about it. That's how many different ways the examiner can manipulate the free radical substitution question. Any questions from your side?
No, sir.
No, sir.